Dear Professor, it's my honor to be here to do a presentation. The report name is a study on the fault detection of real fastener. My report includes three parts. The part one is research background, and part two is real fastener positioning. Part three is real fastener classification. First is research background. With the increase of urban railway transit operating miles, in order to ensure safe operation, and the demand for intelligent maintenance technology is more urgent. And according to the statistical analysis of the cause of the railway accidents, the accident caused by the railway fastener raised 44%. Therefore, the maintenance of railway fastener is extremely important. First, introduce the rail fastener. The rail fasteners are the parts on the rail used to connect the rails and the sleepers. Their function is to fix the rail on the sleeper, maintain the gauze, and prevent the longitudinal and lateral movement of the rail relative to the sleeper. And there are four kinds of states of the rail fastener, and all the conditions are reflected in the clip. The first condition is normal, and the clip is normal, and the three other condition is abnormal. The clip is broken, and the clip is lost, and the clip is displacement. And the rail fastener fault detection consists of two steps. The first step is rail fastener positioning, and the second step is fastener imaging classification. For the first step, rail fastener positioning, since the fastener imaging is small in the captured imaging, so it's necessary to locate the fastener in the captured imaging and crop it to obtain a fastener imaging. And after obtaining the fastener imaging, the imaging features are obtained by imaging processing technology, and the state detection is realized by combining with classifier. And part two, rail fastener positioning. For the rail fastener positioning, their pixel statistics is a traditional method. First, grayscale the collect original imaging, like this. Then, by counting the cumulative gray value in vertical direction, the cumulative gray value, and we can get this figure. And the threshold can be selected to locate the real condition. And by counting the cumulative gray value in horizontal direction, a threshold, this is the figure. And the threshold can be selected to locate the sleeper position. This is the real position, and this is the sleeper position. And the intersection is the fastener position. And we can get the fastener position from the captured picture. And this is another traditional rail fastener positioning method called global template matching. And the manual collect fastener imaging is called a template. We can first get a template, and the template is used to scan in the imaging in both horizontal and vertical dimension to obtain a subregion of the figure. And we can calculating the similarity between the subregion and the template. The subregion with the largest similarity is selected as the fastener position. And we call this kind of method global template matching. For the two traditional rail fastener positioning method, for pixel statistics, the pixel statistics method can actually realize the fastener positioning in the ballast rails. But the fastener positioning effect for the ballastless rail is poor. The reason, when pixel statistics method applied to ballastless rail, the pixels grayscale changes in the vertical direction are small, which will lead the threshold to get the slipper is hard to find. When this method used in ballastless rail, this threshold is difficult to get. And for the global template matching, the template matching method can be applied to both ballast and ballastless rail. However, the traditional template matching is scan picture in the 2 dimensions. So this positioning method will have has errors in 2 dimensions. And we propose a double template matching. First, the rail template is used for rail positioning, and then we can get a rail area map, include the fastener and the rail based on the prior site knowledge. And then the fastener template is used to locate the fastener in the RAM, the rail area map. Due to the large difference in gray value between the rail and the background in the picture, there is no error in positioning the rail. Therefore, there is no horizontal error in the RAM map. And because the fastener positioning, and this is the RAM, rail area map, and this is a fastener template. And because the fastener template positioning in the second step is in the RAM and only searched in the vertical direction. So this method has errors only in the vertical direction. And this is the flowchart of the double template matching. For rail positioning, first, for the original track imaging, we can do the gray processing. And the squared Euclidean distance is required to calculate the similarity between the rail template and the imaging. And we can get the rail position. And with the prior site knowledge, for example, the width of left and right fastener and the width of fastener, we can get a rail area map, only include rail and the fastener. In the second step, we use the fastener template and RAM. We first do the imaging processing, include histogram equalization and Gauss filtering. And then normalization correlation coefficient is adopted to calculate the similarity between the fastener template and the RAM. And at last, we can get the fastener position. And this is the comparison of fastener positioning method. The track line is the ballastless track, and the method is 2 traditional method, and this is the proposed method. Originally imagine the total number is 631, and this is the successful positioning imagine number, and this is the accuracy rate. It can be easily found out. The proposed method have the best performance. And this is the positioning result of the second step of the proposed method. This is the rail area map, and the fastener position only searched in the vertical direction. So there is no error in the horizontal, only have error in vertical direction. After finish the rail fastener positioning, and then do the rail fastener classification. The classification based fault detection of rail fastener firstly needs to acquire imaging features. And the 2 most used features are the histogram or oriented gradient and the local boundary pattern. The first feature, HOG feature, can describe the edge feature of the imaging, and which is more conducive to detecting the displacement state of the rail fastener clip. Edge feature is conducive to the displacement state of the rail fastener clip. And the LBP feature can describe the text feature of the imaging, and which is more conducive to detecting the broken and lost states of the rail fastener clips. The text feature is conducive to detecting the broken and lost states. The above 2 features, HOG and LBP, are also called artificial design feature. Existing research so that such artificial design feature extraction is sometimes insufficient. As we all know, deep learning algorithms have stronger feature representation capabilities. For example, the autoencoder and the restrict Boltzmann machine. The autoencoder aims to reconstruct the input information, which can give a better feature description, and it tends to represent its feature when applied to the fastener imaging reconstruction. And for the restrict Boltzmann machine, consists of a layer of visible unit and a layer of hidden units, and has powerful feature representation capability, and it tends to represent text feature when applied to the fastener imaging reconstruction. And this is the result. This is the imaging feature reconstruction of the real fastener. This is the reconstruction map of the features obtained by autoencoder. And the edge of the fastener can be clearly seen in the picture. If the clip is displaced, the change in this character will be obvious, and we can easily find the fault. This is the reconstruction map of the features obtained by restrict Boltzmann machine. The many similar points in the figure are the text feature of the fastener. If the clip is missing or broken, the change in these characteristics will be obvious, and we can detect the fault. So, except for the feature extraction problem and for the real fastener detection, there is another problem. The track fastener is composed of two parts, clip and bolt. Clip and bolt, two parts. The state of the fastener is mainly reflected on the clip. All the conditions are reflected in the clip. And the different angle of the bolt will cause false alarm. So for example, if the whole picture it will be detected as abnormal, and if only use part of the picture, this will be detected normal. So a segmentation of the fastener imaging is required before modeling. And this is the flowchart of the proposed detection method. For the real fastener imaging, first we use automatic segmentation to get the real fastener clips subgraph. And then we use AE and RBM to get the feature and fuse them together, because we want to use the edge feature and the text feature. And we will calculate the Mahamlas distance and get the threshold. For online detecting, first we do the automatic segmentation and obtain the feature and fuse them and calculate the distance. If the distance exceeds the threshold, we can find that the real fastener is abnormal. If not, the fastener is normal. And this is the comparison of the detection results. And we compare the left real fastener and the right real fastener. This is the full compared method. We compare the false alarm rate, missed alarm rate, and the error rate. This is two traditional methods, AE and RBM. We can find they have a little higher missed alarm rate. By integrate them together, we can get DFFN, and we can find the missed alarm rate is 0. But it still has a little high false alarm rate. And we use segmentation, and we can reduce the false alarm rate to get this. And this have the same phenomenon. And the proposed method have the best performance. This is the conclusion. And for the real fastener positioning, we propose the double template matching. The proposed method only has arrows in one dimension, which can effectively improve the positioning accuracy. And for the real fastener classification, we propose the local depth feature filter network. The proposed fastener classification method can effectively reduce the missed alarm rate by fusing acquiring managing feature of AE and RBM. At the same time, it can effectively reduce the false alarm rate by eliminating the interference of the bolt. And that's all. Thanks for your listening. Thank you.